This video is part 2 of periodic trends. In this video, we're going to be dealing with ion size as well as ionization energy. In part 1, we dealt with atomic radius and electronegativity. Okay, so let's start off with it. The trend that we're going to be talking about today is the trend called ion size. And with this trend, this definition might sound a little bit familiar. It's half the distance between the nuclei, but instead of atoms, it's of ions. And we did talk about ions previously. Remember, an ion is either a positive or a negative atom due to the loss or gain of electrons. If you lose electrons, you become positive. If you gain electrons, you become negative. All in order to have that stability achieved by having noble gas electron configuration. Our trend on the periodic table, as we go down the periodic table, our ion size increases. And this is the same reason as the reason we gave for atomic radius. We have more electrons in higher energy levels. Even though we've lost electrons in the metals and we've gained electrons in the nonmetals. We'll talk at a different day about the difference between a neutral atom, we call it a parent ion, as well when compared to its own ion. But for now, we're just going to talk about ion size increases down the periodic table. And then again to the right, the opposite holds true. We decrease to the right due to more protons, that increased nuclear charge. So now we can ask questions once again about ion size. So here's our sample problem. It says, which of the following ions has the greatest atomic radius? And we're given the lithium ion, which is right here, the beryllium ion, the sodium ion, and the magnesium ion. So we're looking for greatest radius. Okay, so it increases down, so that means lithium and beryllium are off the charts. And then it decreases to the right due to increased nuclear charge. So we have sodium ion being the largest of those 4 ions. Okay. And our last trend that we're going to deal with today is ionization energy. Ionization. So this is going to be the amount of energy required to remove an electron from an atom. To remove an electron. And we would expect atoms that easily give up electrons are going to have a very low ionization energy, and atoms that do not give up electrons will have a high ionization energy. And so here is our trend. As we go down the periodic table, we see that ionization energy, oops, let's start that over again. We'll say ionization energy decreases. Those electrons are further away from the nucleus of the atom, that positive pull. They have a lot of shielding going on in between. And so ionization energy decreases going down. And as we travel to the right, ionization energy increases, which would be expected. Alkali metals in group 1A would have a very low ionization energy. They easily give up electrons. Same with alkaline earth metals in 2A. And then we have these atoms over here on the nonmetal side, like neon and argon, which definitely don't want to give up their electrons. So let's take a look at a sample question that we can deal with. It says, which group has the greatest ionization energy? Alkali metals, alkaline earth metals, halogens, or noble gases? So remember, ionization energy will decrease down, but because these are group trends, we're looking for groups. And it's going to increase to the right. Alkali metals are 1A. 2A is going to be alkaline earth metals. 7A, there's our halogens. 8A, there's our noble gases. So if this value increases to the right, whoever's furthest right is going to have the greatest ionization energy. That would be our noble gases. They definitely do not want to give up an electron. So there we go. And that is the second of 2 videos. We talked about ion size, we talked about electronegativity, we talked about atomic radius, and we've talked about ionization energy.